Hello, here I am recording the substance, the main things that you need to know for the water module, and this would be the first installment for that water module. Alright, we actually got into this a little bit already, but I'm going to start from scratch on the water module. And so the first thing that we want to specify is what it is we want to accomplish, what we need to accomplish in order to have an efficient allocation of surface water. And when we get to the groundwater, it's not going to be that much different, but we're going to focus first of all on the issue of diverting water from a stream or a lake. All right, so one of the things that we need to have in order to have an efficient outcome is equal marginal net benefits. What exactly does that mean? Well, let me flash a graph up here. Get that right up to my nose. Hopefully you can see that. All right, here's just your most basic economics graph with your marginal cost line, which is usually the supply line. Okay, sloping upward. Okay, that means the total costs are rising at an increasing rate. Okay, and then the marginal benefit line slopes downward. That means that total benefits are rising at a decreasing rate. And normally the optimum is where they intersect, and indeed that is the optimum still, but unfortunately with water there may be a quantity constraint so that we can't get everybody to where marginal benefit equals marginal cost. So what we'd like to do then is to have everybody have the same gap. We call that gap marginal net benefit, the same gap between marginal benefit and marginal cost. And the A subscript means available. So the marginal cost difference between that and the marginal benefit for what's available should be equal across all users. And it comes back to the same thing we talked about under pollution and emission allowances. We need trade. We need to move the allowances. We need to move, in this case, the water rights, as long as the marginal net benefit in this case, in that previous case, marginal cost, differed, because then there was an opportunity to gain from trade. And by the way, that's exactly how we need to accomplish that, is through trade, because only the users themselves know exactly how fast, I'm getting a little out of sync here with the reversal here, how fast the marginal benefit declines with quantity, okay, and how fast their marginal costs increase with quantity. Only the users themselves know that. That information is highly decentralized. That is, the central authorities don't know that. There's no way for them to centrally allocate water in a way that's going to come out to maximize the net benefits across all uses. All right, so anyway, so we want the marginal net benefits to be equal across all uses, and really the second criterion is just an outgrowth of the first one, namely the availability varies over time. All right, so given that that's the case, we want the marginal net benefits to stay equal, maybe not at the same number, probably not at the same number, but to stay equal across users and across uses with changes in the availability of water from drought to flood. Flood, I guess, is a combination between a flood and a drought. From flood when water is very abundant to drought when, who's going to get cut off first and by how much? See, all of that can be resolved through trade if we have clearly defined water rights and clearly defined prioritization of those water rights. Let me hasten to add, I'm not talking about prioritizing water uses like municipal and commercial, industrial. In fact, some places do that, and it's a terrible mistake, and it's one of those normal outgrowths of the political process because it seems to make sense. Sure, municipal has higher value uses than probably any agricultural uses, but then to say, okay, we're going to make sure that all the municipal uses are met before any of the agricultural uses are met at all, that's a huge mistake, because what that says is that the last drop in municipal use is worth more than any water applied to agricultural use, and that's just definitely not so. So that balancing act of exactly how much goes to different uses has to be resolved by trade. There's just no way for the authorities to know the rate at which the marginal benefits decline for different water uses and water users. And so only the users themselves will know when their marginal use of water, some marginal acre feet or gallons of water, are best served by them using them themselves or selling them to somebody else at a market price that they can observe, or an offer that's been made to somebody, that's been made by somebody to them. All right, okay, so the second criteria then is to keep the marginal net benefits equal over time, and that takes prioritization of users' actual rights, and then those rights need to be divisible, so that if you, for example, if you purchase 100 acre-feet of right to divert or use water, that you can keep 70 of those and then sell 30 of those to somebody else. That's what we mean by divisible. Okay, and then sold on a willing buyer, willing seller basis, perhaps through a market, ideally so. One of the things you discover pretty fast about water is that maybe inherently, maybe because of all the restrictions and how governmentalized it's become, the water markets are kind of thin, which means that there aren't that many transactions, which means there's not enough volume. I don't mean of the water per se, but number of transactions, to some extent the volume of water, to establish a going rate, a firm rate at which you can expect to either sell water or purchase water. All right, so again, this is exactly analogous to what we've been doing all semester long, selling habitat preservation credits, selling emission reduction allowances. Same basic idea. Information is decentralized, and plus we need an incentive mechanism to motivate users to consider whether their water uses, in this case, are worth as much as somebody else's water uses, and that market price then, or an offer from somebody, is the incentive to say, my water uses aren't quite as valuable, at least for some of my water, as somebody else's. So I'll sell them some of my water access. That'll increase my marginal benefit of water use. That'll decrease theirs until we no longer have any reason to trade further. All right, so we have year-to-year variability in water use and water availability. Use as well, because when it's raining a lot, we don't use as much water for landscaping. We don't use as much for irrigation and agriculture, but mostly the water variability is from the supply side. So that's why we build reservoirs, okay, to mitigate that somewhat. But even in most places, even with reservoirs, there are times when you have to decide, hey, who's going to get cut off? We don't have as much water this year as we did last year. We can't do all of the water uses this year that we did last year. How are we going to curtail? Okay, so again, we don't want to prioritize uses, but we do want to prioritize particular water rights, pieces of paper that say you are entitled to, by holding this, by being the owner of this piece of paper, to divert 10 acre-feet of water from a certain water source each year if the water is available. Now, what does that mean? Well, it depends on the priority of your use. That can be done, as is done in many western states, mostly western states, because that's where water availability is more constrained, through the prior appropriation doctrine. And that just means that the priority of your water use depends on how senior it is, how old that water use is. So, for example, the piece of paper you may hold says, this water right was established in March 25th, 1875. Well, a long time ago. Well, depending on where you are, or that could be one of the first ones, and so that water right may never ever be curtailed. In the worst case scenario that anybody can imagine, that's the highest priority water rights. It was probably created in 1875 to facilitate somebody grazing animals. Today, probably the lowest value water use, and clearly if this water right, March 25th, 1875, is saleable, it's going to gravitate to very high value water uses, users of water that value absolute, total non-interruptibility. Okay, so with the prior appropriation doctrine, we can accomplish that prioritization of water uses by first in time, first in right, and then people recognize when they're buying and selling water rights how senior, how certain, how uninterruptible, or if it's not so senior, how interruptible this water right is. And of course, these different water rights have different prices based on people valuing non-interruptibility, or saying, well, every so often I could use some water. If it's a dry year, the world's not going to end if I get cut off. So I'll buy the cheaper junior water rights that get interrupted periodically. Right, so you can have the prior appropriation doctrine over time, establish water use priorities, And or you can, if you don't have that available, or you have problems with water use availability, and you don't have the prior appropriation doctrine as a way to prioritize, you can just create different water use classes, not uses. Okay, like agriculture and municipal. And no. We mean you are the holder of a Class A water right. Okay, this water right will never, ever be interrupted in any conditions that have ever occurred in this place. It is the top priority one. The B water rights, well, they're pretty certain, but in a 100-year drought, yeah, you're going to get cut off. This water right's not going to we're not going to be able to honor this water right under those conditions. Okay, so then further on, C, B, D, and so on. And so if you set up water rights like that, you could auction them off, right? And the Class A water rights are going to fetch a higher price at the auction than the Class B water rights, and more than the Class C water rights, and so on. So prior appropriation doctrine has already set the table in a lot of places. In places like here in San Antonio, Texas, where that hasn't happened, what could have been done wasn't done, but what could have been done when we decided that the Edwards Aquifer was now a scarce water resource, that pumping was likely to exceed the amount that we would like to pump out of it every year to keep the springs flowing. We could have done that. In other words, we could have just said, okay, we need to quantify water rights now. We need to get away from Texas's rule of capture. And so we're going to create these different water right categories, and we're going to auction them off. As you can imagine, people aren't too thrilled to have to purchase water rights when that's something they've always had and they've exercised. So therein lies the political reason for having done what we did, which is still evolving in the sense that you have to prove that you are a beneficial user of water, and then you get a water deed, sort of, in this area. And then if all the water deeds add up to more than we want to pump, then we have to have some way to constrain that downward. You might recall that that was an issue back when we talked about pollution, right? If we distribute the emission allowances to the emission sources according to their past emissions, that may create more allowances than we would like to have in existence, and then we need some mechanism to bring that number back down. So again, prior appropriation doctrine, not preferential use doctrine. We'll talk about that in a minute. Prior appropriation doctrine is a good way to keep the MNBs equal over time as water availability varies. And if that's not possible, then some sort of an auction scheme, maybe not through money because of the politics, but some way of distributing different classes of water rights, so that people know, based on the little piece of papers that they're holding, how certain and how uninterruptible their water rights are. All right, I'm going to consult my notes here so we can move on. By the way, I'm following the PowerPoint, not looking at that here. I took some notes based on that. But what you should do is you just should definitely look at the PowerPoints. We get into class, we'll kind of page through those. But we're doing this in part because we want to lower the cost of non-attendance. Some of you struggle to do that, so trying to do that, and so follow through that PowerPoint, listen to this. And one of the nice things about when I hold up one of these is you can freeze this later on and stare at this graph a little bit longer than I'm holding it up here. So make sure you do that. If I yank this away before you're ready to no longer look at it, click, freeze that frame back with the graph showing, and study it a little further. And make sure all graphs, all semester long, are first studied, first thought about, and then close the book, close the notes, turn off the video, pull out your graph paper. Pull out your graph paper. So you get my finger here on the screen. Pull out your graph paper, and then redraw the graphs yourself and tell the story that it told. And if you can't do that, see, that's kind of a hint that maybe you didn't get it. See, these brilliant videos and lectures, I'm pretending that they are. I'm hoping that they're informative and that they're clear. But they may not be. You may have to play them a couple times, or you may have to scribble down questions for the online forums or for class. All right. So let me consult my notes to make sure that the next item for us to discuss is how do we know when to expand the capacity of our system? And by that I mean we're not going to expand how much water comes down, but to expand the capacity of the system to deliver water on a steady basis, to minimize perhaps the year-to-year variability of water, and thus the struggle to keep those MNBs equal. How do we do that? What's the criterion for doing that? Well, any storekeeper will tell you what it is, but it's useful to go over it in the context of water, and it's something you have to be on top of to project these conditions and to see when they're met, because it takes several years to build a water project. Okay, so what conditions should you be looking at? All right, so you should have a price mechanism to make sure that the amount of water available right now is not overextended. In other words, to make sure there aren't any shortages, right? So you raise and lower the price as necessary in the short term. Either a water rights market will do that, right, just by supply and demand, or if you're talking about somebody like San Antonio Water System, in fact, let's just do it in that context, San Antonio Water System. How should they decide when to add on their capacity to deliver water to San Antonio? Some water project or another contract to buy water from somebody, build a pipeline, build a dam, something. How should they decide when to do that? Okay, so they should set the price in the short run to ration out the amount that's available. All right, and in the long run, they need to project that price. Okay, so they need to be looking forward, saying, okay, fine, right now, $100 an acre foot, that's a number I pulled out of the air, is enough so that the amount supplied and the amount demanded are equal. And I definitely don't want the amount demanded to be more than the amount supplied. You turn the faucet, you want water to come out. Okay, so anyway, 100 acre feet is about right to keep the quantity demanded and quantity supplied in the neighborhood. If we charge less than that, we'd have shortages. If we charge more than that, well, we'd be just ripping people off because of monopoly power, right? So there's your rationing price, $100 an acre foot. If you project that price over time, 5 to 10 years, however long you think it would take to add the next available, next cheapest supply into the system, okay? So project that price forward that number of years, the amount of time it'll take to add to the system's capacity to deliver water. And when that rationing price, the price needed to keep the quantity demanded and quantity supplied equal, when that exceeds what it'll cost to expand the system. Start expanding the system so that 5, 10 years down the road, you'll have expanded the system and avoided having a rationing price that's higher than what it costs to have additional water available. Right? Makes sense? Why did I say a storekeeper understands this? Storekeeper says, how should I decide when to put some more stuff on the shelf? Well, when it'll sell for at least what it costs to put it there. Right? So if we do this, projecting forward what the rationing price will be given the current capacity, right, we're basically doing that. We're asking, okay, I have to keep raising price to not run out. If I have to keep doing that, at some point, it would make sense to bring in more supply, right? Because the additional supply will sell at a profit for what the going rate is for the stuff. All right, so let me look at my notes again here and make sure that, the next thing up is a graph, and this is going to look a little bit different. And again, it's going to be on video for you. So let me grab which I've got several copies of it over here on the side, and I've got my little thing to kind of stiffen it up a little bit. Whoops. Everything's a little backwards on these screens. Okay, anyway. So there it is. Okay, and by the way, this is identical to the one that's in the PowerPoint, but I have to hold it up here in order to refer to it for my discussion. All right, so let me move my fingers out of the way there to make sure I don't block any of the number. Again, this one is identical to the one that's in your PowerPoint. I can remember which slide it is. It's the first graph that's in that water PowerPoint. All right, so here we have a staircase because water in any given region, call it region M in this case, is a series of additional sources, each one of them with a higher marginal cost than the first one. And so when we have demand 0, I don't know if you can see this. I'm going to keep that hand the same. Demand 0, that's over here. Okay, right there. Okay, demand 0. We have that demand, no problem, right? We have our initial water source, the one that costs $128 an acre foot, right over here, $128 an acre foot. Hold the graph back up there. There's the 128 below my index finger. Okay, and up to 348, up to a 348, up to 300, I have to keep saying that because the screen went blank, up to 348 acre feet a year. Okay, no problem. 128 is the marginal cost. It's constant, so it's equal to the average cost. So if we sell water at demand D0, absolutely sell it. P equals MC is an efficiency criteria. Sell it at $128 an acre foot. 348 acre feet will sell. Your total revenues will equal your total cost, including opportunity cost. Everything is great economically, politically. You know, you're not making money selling water. I'll drop the thing so I can gasp visibly. Yeah, see, that's the thing about politics. It often gets things exactly backwards. Okay? In the political world, if the government is selling water, it's somehow not okay to be making money at it. Okay? And so we'll see in a minute that that's going to be the outcome of certain of efficient policies under certain conditions. But right now, no problem. With demand zero, the efficient pricing policy of P is equal to MC, price equals to 128. Fine. Yeah, you're going to be using every last drop from your first water source, the one that comes in at $128 an acre foot. But for now, it's okay. But suppose you live in a growing area and population plus income is increasing, and demand shifts out to D1 or is expected to do so. And so now it's going to take $248 per acre foot in order for you not to run out. But now what's the problem? Well, from an economic perspective, there's no problem. Okay, and even from a well-informed political perspective, in other words, if all the voters knew economics, were good students of economics, no problem, because you see, the difference between the price of 248 and still the marginal cost of delivering 348 acre feet a year, the 248 minus 128, that 120 difference, that could just go paying, just goes into the city coffers and is an efficient way to pay for cops and firemen, right? Why is it an efficient source? Because it's the result of pricing water efficiently, right? But in the real political world, where not everybody understands economics, this is a difficult situation for the politicos to live with, right? Because they've got a monopoly on water. Okay, and now they're selling water at a profit, and yeah, some households are low income, and so that could be a burden to them. I would argue that a low income household doesn't use enough water for that to probably make very much difference to them, or at least at a $248 an acre foot, they're going to figure out a way not to waste any water, and their water bills are still going to be pretty small. But none of that filters down politically nearly as fast as San Antonio Water System or whoever is making nearly 50 cents on the dollar profit. Whoa! No, we can't do that. All right, so what then happens in order to live with demand conditions D1? Well, it's called average cost pricing. Okay, there are other pricing techniques that we'll go over later in this water module, but one that SAWS has done for years with a little more complexity than we have here is average cost pricing, and by definition then there's not going to be any profit. Now let me switch out to another version of this graph that's got a little more information on it, and you'll see what's wrong with average cost pricing. All right, so there it is. Okay, and let me just let's see, get this to locate well up here. All right, so you see several dots there where it says AC, right there. Okay, and then over here above this index finger, there it says AC. All right, this dotted line with these hand-drawn dots on it where it says 195, 209, 228.5. That's the average cost line that's based on those costs of 348 acre feet a year at $128 marginal cost. And then the next available water source costs $288 marginal cost per acre foot. And then the third and final in this picture is $376. Okay, if we start blending all that together, we can sell at a break-even point at those points there that are called the average cost line. I know this is going to need some some discussion in class, but at least you have this video to go back to with the graph on there and some attempt at explanation here without any feedback and interaction. I understand that's problematical, but look here at this D1 situation where I'm pointing with my finger. Okay, so suppose you have demand D1 and it's not politically correct to be up here at this point, right, where they're making this enormous profit, right? See where my middle finger is pointing there. Okay, that's the efficient point where my middle finger is pointing right there. Okay, selling 348 acre feet a year at $248 per acre foot, and then making $120 an acre foot, 248 minus 128 profit. Okay, which from the city's perspective or the local government's perspective is money that could be made available either to save for future water projects rather than putting a bond out and paying off with debt, or substituting that for tax revenue and pay for the cops and the firemen and other city services that way. Again, that's proven not to be politically correct in a lot of places, including San Antonio. So instead, what we do is we blend the expensive water, the $288 per acre foot water, with the $128 per acre foot. The $128 per acre foot water. Okay, and we get a blend price of $175.8 per acre foot. Now think about what this means. It means we're going to be selling water, and I didn't mark on the, let me go ahead and mark that on the x-axis here. We're going to be selling this much water, which we'll just say this is about, let's just make it about 430. By the way, you can figure out what the exact dollar amount is if you try hard with a bunch of math, but we won't do that. Okay, so this is a 430 right there above my middle finger that you can see there. Okay, right there. Okay, and so what we're going to be doing is we're going to be selling 430 acre feet at $175.8 per acre foot, and we get that shaded area up there, right there, as a deadweight loss. It's not a triangle this time. It isn't always a triangle in the real world. All the textbook versions of it are. But we get this deadweight loss up here because the last 82 acre feet a year, 430 minus 348, that's 82. The last 82 acre feet per year are sold for $175.80, and the cost of delivering them is $288 per acre foot. Clearly not something that any rational business person would do, saying, oh, well, I put this stuff out on the shelf and I'll sell it at a loss and make up for it by selling other things at a profit so that I'll break even. No. I mean, I know there's such a thing as loss leader advertising, but no, we're not talking about that. We're talking about on a continuous basis planning to sell something for less than it costs and just making that loss up by selling at a profit. Other stuff, no. Okay, but that's what's politically correct quite often in water, is to put water in your home that you're going to use because of the price signal that you're given for uses that you wouldn't put them to if you knew what the full cost of that marginal water really is. Okay, so marginal cost pricing can yield a profit in many cases because you've got to signal the high marginal cost of water to deter low marginal value uses. Okay, so again, let me put this up here right on the screen so that it blocks everything, including my face and all the numbers at the bottom. And so you can go back to this later on if you need to and freeze the screen right there so you can look at all the different things on it. And let me just flash up my calculations for the average cost. And so you'll know where the 195 and the 209 and the 228.5 and the 175.8 over here on the side, where those come from. Okay, so and also you might see there down below, down here, there's a little some written there. The pi symbol is for profit. The profit with a P equals MC policy with demand at D1 is what's shown there, 248 minus 128 times the 348. And that can be used to offset city taxes then in many cases it's seen as an embarrassment and a reason to have an average cost pricing, which is, as you can see from the deadweight loss there, see that that's inefficient. All right. Let me flash my calculations up there so that we'll have a record of those on the screen, and then I think at that point I think we're going to pause this for just a minute in order to all right, so let's see, how far back should we do that? Okay, so have a note to myself up there to email the staircase graph, and you can see the different average cost calculations for the different quantities: 492, 600, 708, 800. And the numbers you can't read are not important. That's just a shorthand there to eventually add up what all of that stuff is. And make sure you understand what is being calculated there. How much of each of the different kinds of water summed together and then divided by how much total water it is will yield you the average cost of that quantity of water. Again, fortunately we have a class. We can go over this in class. But again, in case you don't make it, there it is for you, the calculations that went into that average cost line that you saw me hold up a minute ago. All right, so we got that put away. Oh, and by the way, you want to know what that looks like for our San Antonio water system? Here it is. Okay, whoops. See, everything's backwards, and so I'm kind of out of sync there. There it is. See that long, low MC? That's our Edwards Aquifer. Bless that Edwards Aquifer, right? Lots of water, really cheap. Doesn't cost much money to pump it out of the ground. Wow, when we hit that point right there, which we seem to be at, okay, with the growth of this area and the restrictions by the Endangered Species Act on the amount that can be pumped. See, the next available water source, each next available water source, as you can see there where my finger is, whoops, okay, covering it up, right, little staircase there, and it keeps climbing. Each additional water source is a lot more expensive than the Edwards, in some cases a lot more expensive than the previous really expensive compared to the Edwards Aquifer water source. So here we have that challenge big time. If we practice marginal cost pricing, the efficient pricing policy, we are going to make a big, big profit. Again, which is not a problem from an economic efficiency perspective because the city has other expenses. And the other sources of revenue, either taxes or the money that San Antonio gets from the city public service, those are equally problematic, inefficient, regressive. And again, it's not necessarily about truth and economic analysis in the political process. It's about what people believe. And and speaking of that water, the water monopoly notion, let me just pull my graph back for a second with some other information on it. And you'll see that's not what we're talking about, but that will be the perception. San Antonio water system is a monopoly, and if they charge a high price, more than enough then to cover the expenses of actually delivering the water, it will be perceived, probably incorrectly, as a water monopoly being abused. Okay, so let me grab my sheet that shows what a water monopoly would look like. Just sort of a refresher course from your micro principles. Okay, so here's that. And you can see there on the graph, which I'm tilting a little bit so I can still see over it and see what's on it. You see where it says our MR2? That would be the marginal revenue line for demand line D2. Okay, and marginal revenue equals marginal cost right there where it intersects the MC line, the vertical part of it. Okay, so the efficient quantity the efficient thing for SAWS to do if it were a monopoly, okay, efficient from their perspective, would be not to have any water but the Edwards Aquifer water, but to charge a phenomenally high price for it. You see where it says price with D2 way up here? Okay, so if you take the 348, you go all the way up to D2. Let's see, that would be right up here. 348 up to D2, then you go over to the side there, and there's your price, a big price. So that's more expensive than P equals MC, even for the most expensive water source on here. All right, so we're not talking about, see that 248 that I said, the 248 that I said we should charge with demand D1, which would yield a huge price. That's not a monopoly profit. The monopoly profit is much, much, much larger than that. The 248 is just a merely efficient price given demand D1, which, given our wonderful aquifer would yield the water system quite a large excess revenue, a profit. All right. At this point, I'm going to cut off this first water video and take a little break, lubricate my vocal cords, and then I'll be back to record some more. And of course, you can decide whenever you want to see the second one. Hopefully, before our class that we discuss it on, which I understand will be a challenge because I'm just recording this on the same day that our class will cover this later on. Hopefully, they'll figure out a way to have a little bigger lag between when I can make these videos available to you and when you we actually have a chance to talk about them in